So I'm going to give the second lecture to do with extremal numbers. So the main theorem that I'm going to try and prove today is something I mentioned the last day, which is the following. So we have what I want to show is that so for all S natural numbers, there is a natural number t and some c greater than 0, such that the extremal number of kst is at least c times n to the 2 minus 1 over s. Basically, it's the thing I mentioned the last day that if you fix s and you make t as large, you make t pretty large in terms of s, then you can actually guarantee that the simple upper bound we proved yesterday is actually sharp. So that's the aim. Now, there's a few different ways of doing this. So originally, the way it was done is using explicit, what are called norm graphs. But I'm going to talk about how you do it using something called a random algebraic method. And in fact, the proof I give is basically the proof due to Boris-Buch. So for that, I'm going to have to set up some terminology and some setup and notations. So let's start with some setup. So I'm going to fix a prime power p. If you like, you can just think of it as a prime. It doesn't really matter so much, but just also works for prime powers. And let fq be the field of order q. Okay. So what we're going to use to define the graph is we're going to use polynomials over fq. In fact, ultimately, we're going to use random polynomials over fq. So we're going to let PD be the set of polynomials in t variables. So by rights, I should put a t there, but let's not worry too much about that. T variables x1 up to xt with degree at most d. Okay, so more explicitly, what I mean by this is, i.e., or that is, linear combinations, so fq, linear combinations of monomials of the form so all of them are going to be x1 to the a1 times x2 to the a2 up to xt to the at, where the sum of a1 up to at is of ai is at most d. Okay, so to clarify this, let me give an example. So for example, if it's okay. Example, if d is, let's say, 3 and t is 2, let me not write out all of the possibilities, but you're going to get things like x1 squared. We have two different variables, so you'll say x1 cubed, x2 cubed, but you'll also get things like x1 squared, x2, and x1 and x1, x2, and so on. And the point is that you have all of these monomials. They all have total degree at most d, and we just put coefficients in front. So the some coefficient from fq in each of these slots. So it's not a slot. Okay. All right, so what do we mean by a random polynomial? Because I said we could use random polynomials. By a random polynomial, I really do just mean we put random coefficients in each of these places. So we just choose a random element of fq, put it in as the coefficient for each of these independently. The resulting thing that you get from that is that you'll basically get a uniform random element of this, but it's equivalent. So just choose random coefficients. That gives you a random element. Okay. All right, so I want to say a little bit before moving on about the properties of such random polynomials. And I'll prove one very simple property, and then I'll say how it generalizes. So, okay, so what we'll call lemma 1 is if f is a random polynomial from this PD, so random degree d, and x is just some fixed element of fq to the t, then the probability that f of x is equal to 0 is just 1 over q. So essentially, it's saying that so a random polynomial typically will hit about q to the t minus 1 points. And this is saying that it hits every point uniformly in much the same probability, which isn't a huge surprise. Okay, and the proof is fairly simple as well. Okay, so for the proof, I'm going to distinguish a particular subfamily of this family of polynomials. So just the ones with 0 constant terms. So let's let QD be the set of f in PD such that actually f of 0 is 0. So, and that really is just equivalent to the constant term being 0. Now, the thing about this, if I choose this particular family, then everything in the original PD can be written as the sum of something from this family plus a constant. So for every f in the original family PD can be written as f equals g plus h, where g is in QD and h is constant. And actually, what we're actually doing is we're choosing a random polynomial. So if we're choosing a random polynomial in PD, one way to do that is to actually just choose a random polynomial in QD and a random constant independently. And that produces a random polynomial in F. It's still uniform. So all right, so we can choose a random F by independently choosing a random G and H. Okay, but that means that the probability that f of x is equal to 0 is, okay, so it's the same as the probability that g of x plus h is 0. Which is just the same as the probability that h is equal to minus g of x. So I choose these independently. I choose g first. G of x has some value. I don't care what it is. But the chance that h, which I also choose independently, is equal to minus that value is just 1 over q. It's chosen from fq. There's q possible values. So this is just 1 over q. And that's it. In essence, I mean, all that's happening is these equations form a hypersurface. You can take all of this q different parallel hypersurfaces, and you're just choosing the one that goes through it. Okay. So lemma 2 says almost the same thing. So now I'm going to choose x1 up to xm, an element of fq to the t, and they're all distinct. then in that case, the probability that f of x1 is equal to f of x2 is equal to f of xm is equal to 0 is 1 over q to the m. Okay, there's a slight lie here. So it's not completely true. If you're just looking at one point, then it is true that the probability you go through that one point is just 1 over q. You need some small conditions here. So you need, if q is sufficiently large, which is this, and d is at least this, then this is true. So basically, provided your polynomial has large enough degree, you can think of all the points, the probability it goes through all the different points, as being independent. So d depends on m, but basically it behaves like an m-wise independent random variable. The probability it goes through any m points is the same as just if you were choosing it randomly. This was actually known for a long time in computer science. So computer scientists were very interested in these m-wise independent random variables and almost m-wise independent random variables. So this isn't particularly new. I'm not going to say much about the proof of this here. Basically, it's somehow, in essence, a more complicated version of this, where you project down to one dimension. You use that in one dimension. Lagrange interpolation gives this, and then you lift it back up. But I'm not going to go through it. It's kind of believable that if you have a random polynomial and it's sufficiently complicated, then it will go through points independently. Okay. If you're interested, the proof is in the notes. Okay, so that's what we need to know about random polynomials, but we also need to know something about just varieties over fq. So let's let fq bar be the algebraic closure of fq. So standard mechanism in field theory, where you just take any equation over fq and you add the root of that equation in, and then you add all of those and you get the algebraic closure. So algebraic geometry generally works better over algebraic closures. All right, so then a variety over fq bar is just a set of the form. So it's w is the set of x contained in fq to the t, well, fq bar to the t, such that f1x is equal to f2x is equal to fsx is equal to 0, where these f1 up to fs are just some polynomials. So where the fi are polynomials. Okay, and that's a variety. It's a standard thing. You're basically just taking a polynomial, looking at its solution set, and taking the intersection of those things. And this is sort of classical algebraic geometry. Okay, the kinds of varieties that we'll be interested in actually they're slightly different to this. They have some constraints. So on the one hand, we say that w is defined over fq if the coefficients of the polynomials are themselves defined. So if the coefficients of the fi's are in fq. Okay, that seems a pretty reasonable thing to do. So you have these polynomials. You're just saying, so you could think again, you have these monomials, you have these coefficients. The coefficients really are in fq and not in fq bar. And we also say that the complexity of w is at most m if basically the coefficients are at most m. So if, what have I used? The number of polynomials, the degree, and the degree of the FIs are all at most m. Okay, so I have some notion of what it means for the variety of complex. The number of polynomials defining it is small. The dimension we're working in is also small, and the degree of the the coefficients, oh, sorry, I don't need the coefficients, just the degree of the polynomials is small. Okay, so with that, there's a key lemma, so another lemma. I think this one should have been lemma 2. Lemma 3 is the statement that, so I'm going to be interested in the number of points on these varieties. So, and the number of points on these varieties you can measure, one way to measure it is how many points does it actually intersect FQT. So let W be a variety satisfying the things over there. So defined over FQ with complexity at most m. So both of these things are necessary. Then, if that's the case, then the number of points in the variety, so then what we'll call W of FQ, which is equal to the variety intersect FQ, satisfies one of two things. So either it's bounded, so either really it is some constant, and that constant only depends on the complexity of the whole thing, or it's actually quite large. I'm missing, sorry, this should be for Q sufficiently large as well. Okay, so you have this nice property that if you have a variety like this, which is defined over FQ, and it also has this bounded complexity, and you need both of those conditions, then it's the case that actually the number of points on this variety is either constant or quite large. It sort of jumps. And the intuition here, the proof is a little bit harder, and what I'm about to say is kind of a lie, but the intuition is that it's to do with the dimension. So the intuition, which is kind of false, is that WFQ is equal to the dimension, Q to the power of the dimension of W times 1 plus little o1. I haven't defined what dimension is, but every algebraic variety has a dimension. It's kind of close to what you expect from thinking about what happens in the real numbers. And essentially what this is saying, well, either you have dimension 0, in which case you have your constant, or you have dimension 1, in which case this thing is telling you that you're close to Q. You could have higher dimension. You could have dimension 2 or something, but then this is even better. So the fact that this is true is what's called the Langevin bound. The actual situation we're dealing with requires, the Langevin bound requires that this is what's called absolutely irreducible. So that's true for absolutely irreducible varieties. That doesn't say anything about irreducibility, so it requires more work to actually do. So this only applies for what's called absolutely irreducible varieties. Okay, but at least that's the intuition, that basically if dimension of W is 0, then that implies at most constant, and if the dimension is greater than or equal to 1, then that implies that the number of points is greater than or equal to Q over 2. And this is the image to keep in mind. Okay. So these are the two main things. You have this M-wise independence between what's happening. And the second thing is that these varieties produce weirdly unbalanced distributions, that the number of points on the variety is either very small or very large. There's no in between. If you choose points completely randomly, you get a sort of logarithmic tail off. But here, it's up to some constant, and it jumps to some q over 2. All right, so now we can sort of step back to trying to prove the theorem. All right, so let me fix some of the variables. So I'm going to use t, which is the degree of the polynomials, to be 2s. I'm going to use, sorry, this is the dimension I'm working in. The degree, I could probably do with s squared, but let's use s cubed. And what else do I need to fix? Let's say q sufficiently large. All right, so I want to try and define a graph. And the graph, so the classical approach to this just uses a random thing to define a graph to get a lower bound. Here I'm going to use one of these random polynomials. So let G be a bipartite graph between two vertex sets u and v, each of which is just a copy of fq to the s. And what we're going to do is we're going to draw an edge. So we place uv an element of eg if f of uv is equal to 0 for a random polynomial f goes from fqs cross fqs to fqt. Sorry, just fq. So fqs cross fqs is just fqs to the 2s, so that's the dimension that we're actually working in. We're just taking a random polynomial. We're using that to define the edges. And that's it. So was there a question there? I thought somebody.
Are we showing a lower bound for the extremal number of KST? T equals to 2s.
Yeah, so probably I should have used something else in the dimension. So what I mean here is I'm working over fqs to the fqs. So if you think of the original theorem as being this instead, then yeah. I don't think I used this t very much in the lecture anyway, so all right. Okay, so how many edges does this thing have? Well, the probability that uv is an edge is the same as the probability that fuv is 0. And we've done that, right? It's the first lemma, so it's just 1 over q. Okay, so therefore, the expected number of edges in this thing is just the sum of this, so the sum over uv of the probability that uv is in the edge set. And that's just, well, the total number of possibilities is q to the 2s. Probability is 1 over q, so this is q to the 2s minus 1. And if, so each of these u's and v's, they each have size q to the s, and let's call that n. So in practice, it's a bipartite thing with two things of size n, but it's the same up to a constant. So this is actually n to the 2 minus 1 over s. Okay, and that's good. So the expected number of edges is basically what we would like. So what remains is we'd like to show that we don't contain a KST with t large. So let's try and do that. so let's let W, so we finally define a variety, be, so rather let's fix U1 up to US contained in U. You have to, in principle, do the same from the other side, but it's symmetric. So, and let W be the set of V such that f of U1V is equal to f of U2V is equal to f of USV is equal to 0. So that's V and V. This is the common neighborhood of U1 up to US. So our goal, our aim, is to show that for all U1 up to US, this W is actually small. So think of W is the common neighborhood of U1 up to US. Okay, but this is a variety. It's defined using random polynomials. The polynomials have coefficients over FQ, so it is defined. And it also has bounded complexity because each of these is just F. It has degree at most D, so we can apply the theorem. So basically, by lemma 3, we know that either W is less than or equal to some constant depending on the complexity, which itself depends on S, or it's large. This situation is ideal because it's telling us that we're getting some constant which is most depending on S. This is not ideal because it's telling you that actually the neighborhood is absolutely enormous. But what we're going to show is that this can't happen very often. The reason being that because it goes from constant to this large thing can't really happen. So, now, a little trick is needed for that. So what we're going to show first, so let me just say that here. So the aim is to show that W bigger than Q over 2 happens rarely. All right. For this, I'm going to take, so ultimately, I'm going to take OR to be around S squared. And I want to calculate the moment, and study the expectation of the orth moment of the size of this neighborhood. Okay? So what is this thing? This is the expectation of W to the OR is just basically the number of the sum over V1 up to VOR of the probability that F UI Vj is equal to 0 for all I equals 1 up to S and J equals 1 up to OR. Okay, so the neighborhood of this thing, I'm just basically taking the neighborhood and taking all OR tuples that are contained within that neighborhood. Okay. Just to simplify, you have to do some messing around because of degeneracies. Let's assume these are all distinct. But if these are all distinct, then you're getting F UI Vj is equal to 0 for all I equals 1 up to S, all J equals 1 up to OR. And the probability of this thing just follows from lemma 2. So this becomes, at most, the total number of possibilities here, which is Q to the S to the OR. And this thing just becomes Q to the minus ORS. But those two things basically cancel out, right? So this is some big OR of 1. So actually, this expectation is small. The thing that's sort of lurking in the background here is that I need to choose the degree of my original polynomial large enough that I'm getting enough independence that all of these are independent events. And for that, I need my degree to be at least this OR times S, which is why I chose this S cubed at the very start. Okay, so But this expectation of this moment is small. All right, so knowing that, there's actually a fairly simple calculation that finishes. So what I'm interested in is what's the probability that actually this doesn't hold? So the probability that W is bigger than this constant depending on S is, well, if it's bigger than this constant, then it's actually already bigger than Q over 2. So this probability is actually just, we can raise both sides to the power of or, it becomes the same. So it's the probability of this. And now we can use, there's a very basic result in probability theory called Markov's inequality that we use at this point, which says that this is at most the expectation of the random variable divided by the bound that we're above. So this is at most the expectation of W to the or divided by this. So this follows from what's called Markov's inequality. Okay, but this is pretty good. This actually means the probability is very small because this thing on top is just some constant. The 2 to the or is also a constant, so let's forget about it. So this is basically some big O(r) of Q to the minus or. So actually, this is really quite small. And if we now take B, so we have a different random variable. So let B be the random variable counting S tuples with more than CS neighbors, then this the expectation of the size of this thing is at most the sum over U1 up to US in U times the probability that it's bad. Okay, this is extremely small. This is not so large, so this is at most Q to the S to the power of S. This is big O(r) of Q to the minus or. So this is around Q to the S squared. This is Q to the minus or. I chose or to be S squared, so it all just cancels out. So this is at most big O(r) Q to the S squared minus or, which is big O(r) of 1. Okay, so actually, the total number of bad S tuples, so the total number of S tuples whose neighborhood is larger than constant, is just some fixed number. So I can just throw them away. So I throw them away. You have to throw away all the edges touching them, but basically that's it. So if we delete these bad vertices and their neighbors, the expectation of the remaining edges, the expected remaining edges is, well, at the very start we had this calculation for the number of edges, and now I'm deleting each vertex in B, and I'm deleting all of the edges that come out of that, but there's at most n of these. So this is at least n to the 2 minus 1 over s minus big O(r) 1 of n, which is at least this. Okay. That's an expectation, but that means that such a thing actually exists, so you just choose a graph that has this property, and then you're done. Okay, so that's that. All right, so the main thing is sort of the fact that you get this, well, you have the k-wise independence, but you also get this jump in the distribution. If sort of anything comes from this, It's to learn to study distributions that are weird, like this. But yeah.
This proof gives constructs for t greater than something depending on this constant, right?
Yeah, so what it actually shows is that there's no ks and then this function c of s that comes out of this result. Sorry?
Do you know what this constant is, or it's a...
Yeah, so with this particular proof, so I said this lemma that depends on the dimension. The lemma that we actually prove has a tower type band. So actually, this specific proof gives a very bad bounds for this. There's a way to do this that I found later, which just uses dimension as the thing you're inducting on. And if you do that, you get something like s to the s instead, which is reasonable. So, all right. So let me talk just a little bit about some of the other applications of this method. I don't think this is exhaustive. I still think there's probably more to be done here, and further applications of this. But so other applications. So this, as I've written it, is essentially the original rendering of this method by Boris Buch. So a variation that I discovered not long afterwards showed that thing I discussed the last day, which is that this, for theta graphs, this is theta of n to the 1 plus 1 over k, provided L is much larger than k. So again, what we're doing, we're fixing two endpoints, and we're taking L different paths of length k between them, and we know that in that case, so it generalizes even cycles, we get a tight band like this. Maybe a more interesting result is a result that myself and Boris proved after this, showing that for every rational between 1 and 2, there is a finite family of graphs such that the extremal number of that family is theta, so up to constants, equal to n to the r. So what does this actually mean? The extremal number of a family, instead of just a single graph, is the largest number of edges that doesn't contain anything from the family. So as soon as you contain any one of those things, then you hit the extremal number. So this is saying that you can choose a finite family that hits any particular exponent. So I'll say more about that in a second. And the third thing I wanted to highlight, which I pointed out the last day, is an improved band there that x n of kst is theta of n to the 2 minus 1 over s, provided t is at least 9 to the s. So that's a result, another result of Boris Buch's, which uses some elaboration of this technique. The previous bounds, the s factorial bounds, were something like s to the s, whereas this is 9 to the s. Okay, so the last thing I wanted to mention today is a bunch of conjectures, old conjectures of Erdős and Samotij. So some general conjectures of Erdős and Samotij, any of which would be extremely interesting to solve. So the first one, which is what I'll call rational exponents 1, is almost what myself and Boris proved, except what they originally asked is show that this is true for single graphs rather than families. So for every rational number between 1 and 2, there exists some h such that the extremal number is theta of n to the r. So So Erdős offered $300 for this, if anyone's interested. So what myself and Boris did is essentially we showed that there's a single graph for which it's true, but you have to allow all possible degenerate embeddings of the same graph. So there's a bunch of different ways of embedding, and sometimes the vertices are the same, which produces a family instead of a single graph. What one would like to do is do the same thing, but not have these degeneracies. And in some cases, we can do that. So since it used to be that the lower bound was considered the hard part, but somehow this random algebraic method deals with this lower bound very nicely. So now the problem's in the upper bound. So there's been several works on this. So for example, it's now known for n to the 2 minus a over b and n to the 1 plus 1 over ab if b is sufficiently large in terms of a. So this is a result of myself and Oliver Janzer, and this is a result of Zhang and Chu. This seems hard. It's probably, so 5 years ago I thought it was within reach, but it's 5 years later and it still hasn't been proved. So, but I still think it's probably the most doable of these. The second one is what I'll call rational exponents 2. And it says a sort of converse of this. So for all h, bipartite, obviously. Well, actually, it's true for non-bipartite as well. There is some rational exponent such that the extremal number is theta of OR. In fact, they state an even stronger conjecture, which says that there's also some constant here in front, depending on h, such that it's asymptotically equal to that. This seems incredibly hard. If I'm honest, I think it's also false. For example, it's false for hypergraphs. As soon as you go to 3, maybe you have to go to 5 uniform, but as soon as you go to 5 uniform, then this is false. But it's certainly false for hypergraphs. And the other thing is what's called compactness. And this says that for any family, finite family H, the extremal number of the finite family is theta of the minimum over all H in that family of the extremal number. Okay, so certainly the minimum of the extremal numbers is an upper bound, because finding any of them, you sort of win. And this is saying that that should also be a lower bound as well, that if you can ban each of these, then you can ban them all at the same time. Again, this is false for hypergraphs. So this is false for 3 uniform hypergraphs. One of the problems, well, 2 of the problems in the problem sheet are proving that. So, okay, but I'll stop there. Thank you. So the examples you get have some, so